Now I understand, Pierre, that you will make a real introduction to radar remote sensing, to SAR.
Yes.
And then the exercises will be also on radar this afternoon with using Snap.
If it's okay with Snap, it's okay.
Yeah. Okay. So we are here until 5 o'clock, and then there is a coffee break sometimes where you can decide jointly with the students when is the best timing.
All right.
Okay. Thanks, Pierre-Louis.
Thank you. So I can start?
Yes.
All right, super. Thank you, Amalia. So now this afternoon we will be focused on radar, and the acronym of SAR means Synthetic Aperture Radar. It's a special sensor, and I will explain you. This is the sensor which produces image of the surface that is observed. So we are radar begins after 1 millimeter of wavelength for wavelengths higher. We are here in this part of the electromagnetic spectrum when the naturally emitted radiation by the Earth is low enough, and we have the technology to have sufficiently power to highlight the observed surface from the satellite. So radar means radio detection and ranging. And it consists in emitting an electromagnetic waves and receive the backscattered echoes, because the receiving antenna generally is at the same location that than the emitting antenna. It is the same. So you emit a wave in the radio domain, and you range the echoes by order where they arrive to your receiving antenna. And so all the radar from army, police, civilian use with satellite, all the radar are just operating in the same basis. So as I showed you with wavelengths higher than millimeters, this means it is not sensitive to the atmosphere. And here the same area here with optical data, where you see a lot of clouds, and here in the radar you don't see anything. And the other point is, as you give your own illumination source, you are not dependent on the acquisition hour of during the day. You can acquire during the evening. So spaceborne radar remote sensing began in the 70s with in the optical domain, and in radar it begins thanks to ESA. Thank you, Francesco. It began really in radar since 91 with the first satellite that had been launched with radar sensors. It was called the European Remote Sensing Satellite, ERS. And you have continuous radar observation since then. In fact, in 78, you had another radar satellite launched by ESA, which was Jewel, incredible, but it only operates 3 months and got broken. And then we had to wait up to 91. So you will, all right. Something that is important in radar, I will speak later on it also, is the polarization. Because as these waves are synthesized, these are coherent waves, and coherent waves are defined also, are characterized by their polarization. The polarization, in fact, corresponds to the orientation of the electrical angle. the electrical vector, which is always orthogonal to the magnetic vector. An electromagnetic wave is composed by both an electric and a magnetic vector. And when you are focused on the electric field, when you speak about linearly polarized wave, that is the case by the waves that are emitted from satellites, you look at the electric field, and there is a very important plane which is called the incidence plane. The incident plane is defined by the direction of the propagation of the wave and the normal to the observed surface. These two directions define the incident plane. And then you have, when you have an incident, when you have the electric field, which is always contained within this incident plane, you speak about vertical polarization, a wave which is emitted in a vertical polarization. And you can see that the wave, the electric field is not vertical, huh? It is a slant, but it is in a vertical plane. The orthogonal plane is where you get it here. When the electric field is always orthogonal to this incident plane, you speak about horizontal polarization, H polarization. So this is you have to keep this in mind, because polarizations, when we speak about radar, polarization is very important. And this is because we radar use coherent waves, which is the main difference with optic. Optic use the natural emitted waves emitted by the sun, and you have billions of waves that are emitted, and so we don't speak anymore about coherent waves, because even if a sun wave, one wave that is emitted by the sun is coherent, when in a fraction of a second you have billions of coherent waves, and so you don't have waves anymore. You don't have coherent wave anymore. You have the addition of a lot of coherent waves, and it's not the same. So in radar, we speak about polarization because we use coherent wave, and we have two special polarization, V polarization and H polarization for vertical and horizontal polarization with respect with this incident plane. So here are the atmospheric windows. So you see that in the visible part, it's not so nice, but you see that in the radar, in the radio frequencies domain, the atmosphere is totally transparent. This is a really asset, a big asset of radar remote sensing. Here are the different spaceborne SAR sensors that have been launched since ERS-1 in 1991. And so you can see that you have different sensors now, and it's quite comfortable. And these sensors use different bands. A band corresponds to the wavelength. So when we speak about C-band, we speak about wavelengths of about 5-6 centimeters. X-band corresponds to 2 centimeters, and L-band here corresponds to about 20 centimeters. So it's exactly like in optic. When you observe a scene in a different wavelength, you have different information which are complementary each to others. And so you see that from 91, we have continuous observation in the radar domain, especially at C-band. All right, here is just the table showing you the correspondence between these letters characterizing the bands and the wavelengths. These letters correspond. Radar was developed at the end of the Second World War, and it was the military application. And so we kept still military language, which was coding the different bands, etc. But so these bands just corresponds to different wavelengths. And the link between the wavelengths and the frequency is just, they are both are related by the speed celerity. So these sensors gives us a large diversity in terms of wavelength, spatial resolution, and polarization. They all operate either in vertical or horizontal polarization. The spatial resolution range between 1 meter to 1 kilometer, depending on the acquisition mode. The temporal revisit until Sentinel, up to Sentinel-1, we had to wait about for 1 month. Since Sentinel-1, which is the biggest revolution in the field, we have an image of 20 meters of spatial resolution with 6 days of temporal revisit, up to until last month, where Sentinel-1B is out of service, and we are waiting for the Sentinel-1C, which will be replacing. Only Sentinel-1, you don't have 6 days, but 12 days. You have to do 12 days of revisit time. So this is for Sentinel-1, and here is the revisit plan between the temporal revisiting frequency between 6 days and sometimes more, up to 24 days on some part of the globe, because even if you made the acquisition, you have also to store the data on board, and so sometimes you don't have data every 12 days. Maybe now I'm wrong, Francesco, and you have 12 days everywhere on the world. Francesco or Amalia, do you know? No, I'm alone on my ship.
Pierre-Louis?
Oui?
Sorry, I just didn't hear the question.
Yes,
you
yes.
Don't mind?
Is every part of the globe is acquired at 12 days of revisit time with Sentinel-1A, or you have still some part of the globe with 24 days of revisit time? If you know, I don't know.
Right now, no, but I can check.
Well, yes, it's not. It's not so important, but it is at most 24 days of revisit on a small part of the world. Over Europe, every 6 days if you have 2 satellites, and now we just have to wait for Sentinel-1C, and we have 1 observation every 12 days. Here, a table summarizing all this information. So you can see the different name of the sensors, the operating band, their operating period. And here, when you have the polarization mode, you have always 2 letters for horizontal and or vertical. Why 2 letters? Because the first one corresponds to the emitting wave, and the second one corresponds to the receiving polarization in which you record the backscattered echo. So here with ERS1, you emit a vertical polarized wave, and you record the vertical polarization that is backscattered. With RadarSat, it is horizontal for emitting and receiving. And for example, with Sentinel-2, over the land surfaces, you have VV polarization and HV. You have both polarization. So it emits in H and receiving V, which is exactly the same that than if it was emitting in V and receiving in H. in fact, it emits in V and it receives in vertical and horizontal, so VH and VE. So now I will speak about radar imaging and how a radar process an image and the characteristics of the image and its spatial resolution and pixel size. Some other words on polarization, about the sensitivity of radar response over lens surfaces, effects of relief and speckle and filtering, and so. I continue. You have some question? Everybody is okay? Everybody is radar friendly? So, radar imaging and spatial resolution. So, a first basis to know, it's the aperture of an antenna. An antenna radiates in an angle which corresponds to the ratio of the wavelength in which the antenna operates and its dimension in the orientation of in the plane in which you are focused. So, for example, here I made some application. So this is the angle, and now when you have an angle, if you want to know this distance, this distance is just the angle multiplied by the radius between the distance between the antenna and the distance where you are. So, for example, when you have for an airborne sensor, if you have a 4-meter antenna and you operate at X band, 3 centimeters of wavelength, you have here, if you are at 4 kilometers of altitude, you have 30 meters of spatial resolution. With ERS, for example, 10 meters of length for the antenna, about even more than 800 kilometers, with C bands corresponding to 6 centimeters of wavelength, and you have a spatial resolution of more than 4 kilometers. That is far from enough if you want to, if you are interested in lens surface observation at local scale. So how does radar acquire an image? This is the the radar is going in this way, and at one position it emits a wave. So here the speed of the satellite is about 7 kilometers per second, and the wave it emits is 10⁸ meters per second. So you can make the association that when it emits and the wave, which is backscattered, return to the receiving antenna here, as if the antenna was didn't move and was fixed. So it emits a wave which travels, highlights a swath, and when it propagates here, when the wave encounters some objects, these scatter the waves in all the direction, and there is a backscattered wave, a backscattered echo, which reach the antenna, and you classify the echoes, you range the echoes according to the time they are arriving. And so then the next pulse, the radar moves, and there is a next pulse. The the frequency of the pulse is called the pulse repetition of the pulse repetition frequency. So each pulse corresponds to a line of an image, will form a line of an image, all right? And so the spacing between two lines are just the distance that the antenna is done between two emission of pulses. You have two special direction with an antenna, range direction or transversal direction, which corresponds to the propagation of the wave of the pulse, and the azimuthal direction, which corresponds to the move of the sensor. So the azimuthal direction corresponds to the line, and the range direction will correspond to the column of the image. With what I told you with the aperture of an antenna, here the resolution of one spatial resolution on the ground is just the wavelength divided by the antenna, the length of the antenna, multiplied by about 800 kilometers. And so if you look at what it gives, the azimuthal resolution corresponds to more than 4 kilometers. While the pixel size, the distance between two lines, it's just 5 meters because if you use a pulse repetition frequency of 1 kilohertz and a half, and with a speed of 7 kilometers per second, it's really easy to do this. And in that case, to have such pulse repetition frequency, it's very easy. And so in that case, you get line spacing of about 5 meters. This is very important because a lot of people make the confusion between spatial resolution and pixel size. Because in optical domain, when the spatial resolution, what is it? The spatial resolution is the smallest distance allowing to discriminate between two objects on the ground. And so if you have a spatial resolution of 5 meters, so if you have two objects distant separated by 5 meters, you will be able to discriminate them. If lower, you cannot. If you have a spatial resolution of 5 meters, and you put this image you put this acquisition in an image with pixel size of 10 meters. At the end, you will have a spatial resolution of 10 meters because your pixel size is coarse, and so you have degraded. It's not necessary to have such fine spatial resolution. This happens in optical remote sensing. The spatial resolution is slightly lower than the pixel size, and at the end, with optical data, remote sensing optical data, or with cameras, numeric cameras, the pixel size corresponds to the spatial resolution. But in radar, it's different because the spatial resolution is lower. Is much larger than the pixel size. All right. So this is a little different and perturbs some people, but just keep in mind that it's not the same. You know, it's exactly if you have a bad picture, a bad photo, you don't have enough details. You put it in an image software and you create a lot of pixels. All right, you will have much more pixels on your image, but you won't see any details more. It's exactly the difference between pixel size and spatial resolution. So here we have a very nice pixel size, but it's not very necessary because the spatial resolution is about 4 kilometers. That is far from enough. Now, when you look at what happens in the range direction, So the antenna is moving like this. This is a pulse that is emitted and with a certain width. And this width determines the range resolution. So this width corresponds to the pulse duration, the tau p, and multiplied by the celerity of the speed of the propagation. And the factor 2 corresponds to the what do you say? One way back of the pulse. All right. This when you are in a monostatic case, when the receiving antenna is the same than the emitting one, you have always this 2 factor corresponding to one way back of the wave. So the range resolution just depends on the pulse duration, and the pulse duration is just when you make some signal processing, you see that the bandwidth of the pulse is just the inverse of the pulse duration. So this is okay. And so when you do this with a pulse duration with ERS sensor with a pulse duration of 37 microseconds, you have a bandwidth of 30 kilohertz, and in that case, you won't have a big range resolution fine enough. So in that case, as the wave is built, is synthesized, it is chosen to build a wave with a large bandwidth, much larger, and by artificially increase this bandwidth with the same duration from 30 kilohertz, 15 megahertz. In that case, you increase a lot the spatial resolution of about 10 meters. So in that case, 10 meters is okay to observe surface at local scale. And yes, now this is the range resolution in the natural direction of propagation of a radar, this direction. But we are interested in the surface here, which is considered as flat and horizontal. And so how can we project this slant surface over this horizontal surface? It is just with some trigonometry, and you just have to divide this direction, this distance by the sinus of the angle here, what is called the incidence angle. The same here. Suppose that the radar is moving in the perpendicular to the plane of the slide. It emits a pulse like this. This is the width of the pulse. And now, if you want to know here what is this distance, you just have to divide by the sinus of this incidence angle. All right. And so you will have a natural distortion when you look at some radar images, because the incidence angle here is not the same than there. For example, for Sentinel-1, here you are in near range. We speak about the near range because it's the smallest, the nearest range, and far range. Between near range and far range, you are 30 degrees of incidence angle here and 45 degrees of incidence angle there. So the sinus, the sign will move a lot, and the range resolution will change a lot, because this is just given by the system parameters, and this distance will change according you are here or there. And so you have a natural distortion with radar geometry. So when the pulse is increased artificially, you get a 10 meter of resolution in slant range. And when you project it on ground range, you get, just by dividing the sinus, the sine of the incidence angle, you get 25 meters of spatial resolution in the ground range domain. So you always have these specificities that can be seen in the metadata of Sentinel data. You have always range resolution and ground resolution. This corresponds to the natural geometry of the radar. This corresponds to the geographical area, and we are interested in geography to observe the Earth. And now, what happens? You emit with a certain pulse. This pulse will highlight the swath, and it will go back, and then the backscatter's echo. You again sample it, and sample frequency is very cheap to do, and this will give the columns of your image. So, for example, for ERS, the sample frequency is about 20 megahertz. That gives 8 meters of spatial of pixel size in range direction, and if you project on the ground direction from 8, you get 20 meters. That is quite okay. So I think this is summarized here. In the azimuthal spacing, you have what's the same? No, ground range pixel size. When you in the range direction, you have pixel size defined by the sample frequency, a ground range pixel size depending on the sign of the incident angle, while in the pixel size in the azimuthal direction, the line, the pixel size depends on the speed of the satellite and the pulse repetition frequency. What about the spatial resolution? In the range direction, it depends on the bandwidth of the pulse. This is for range resolution. If you want to find the ground range, you divide by the sine of the incident angle. And the azimuthal resolution depends on the length of the antenna and the wavelength and the distance between the antenna and the surface observed. So what about, for example, ERS? You see that in you see that in range direction, it's okay with the bandwidth that has been artificially put. It's okay. You have a ground resolution of about 25 meters, a pixel size of about 25 meters. This is quite okay. In the azimuthal direction, in the line directions, you have a pixel size of 4 meters, or okay, but an azimuthal resolution of about 5 kilometers, that it's far from enough. So this has been improved to improve this resolution. And how do we do it? As the radar emits its own wave, and this is a coherent wave, we have some powerful signal processing tools which allows us to improve this resolution. Just here, I made some simulation. This is an ideal scene with totally dark and with some point target scattered here. And when you emit a pulse, and the radar goes like this, and it emits on the side looking, you see this is what it sees. And now, if you change the pulse and you increase the bandwidth, you see that you have improved a lot the spatial resolution in the range direction. But in the azimuthal direction, you have not improved anymore. And this is really, it's not applicable for Earth surfaces. So you will see this, I will show you an image on a movie made by the CNES to summarize. And this comes from this. And so here is the raw data, when you just send the pulse. And when you use the bandwidth of the pulse, you have increased the resolution in the range direction, but absolutely not in the azimuthal direction. How can we improve the spatial resolution? In fact, you just use the bandwidth of a target that is seen numerous times during the exposure time of the antenna. First, the antenna has an aperture like this, very wide, and so it will observe the same target for a long time. And in the same way than a car with a motor, when you move and you emit a certain frequency, when you move, what you receive is the sound or the wave with another frequency that has been shifted due to the Doppler effect. And this Doppler effect introduces a bandwidth, and with this bandwidth we can do exactly the same then in the other direction and improve the spatial resolution. And the analogy is, instead of looking one target numerous times for a long time, we just process the things as if it was this huge antenna here that was one antenna and illuminate just once this target. I told you that the resolution depends of the length of the antenna. So here, I told you here it's about 5 kilometers. This distance exactly the same that this antenna, fictive antenna. And so this corresponds to about 5 kilometers, and you success to improve a lot, because now you have a spatial resolution of about 10 meters. So this is the synthesis aperture radar processing. You have synthesized another aperture radar, which is much longer, and so with a much narrower aperture. So in that direction, what we use is the bandwidth of the pulse that have been introduced, built with the pulse. And in the azimuthal direction, we use the natural bandwidth, which is the Doppler bandwidth. And in that case, so after using the bandwidth of the pulse, and now if I use only the Doppler bandwidth, I have increased the resolution in that direction, not in the range direction. And when I do both, I get this scene. So you can see that I arrive to discriminate some targets, but other ones, for example, these two, are smaller and smaller even than the spatial resolution after azimuthal syntheture aperture compression. So this is a raw data. When you use the bandwidth of Doppler, when you use the bandwidth of the pulse that you have built, and when you use both. So it's quite magic, but it's nice to take benefit of this. So in that case, by the use of, so this is why we speak about SAR, synthetic aperture radar, to improve the spatial resolution in the azimuthal direction. So in that case, now everything is okay. I have an azimuthal resolution of 10 meters here. For example, if with TerraSAR-X, I get 1 meter in azimuthal resolution, 3 meters in ground resolution in range, and with pixel size, it's okay. Just to show you some illustrations, some different, due to different acquisition mode, you can have different spatial resolution, different swath. So here, a swath of about 500 kilometers, and with a 550 meters of spatial resolution. Here, 30 meters of spatial resolution. The same with 150 meters of spatial resolution. And this one was ERS images. We worked for decades with this, only with this image, and you don't see a lot of things. We will see later why you have all this noise. And with TerraSAR-X, you get some 3 meters. No, excuse me, it's not TerraSAR-X, it's airborne data. You can have a 3 meter of spatial resolution that you can compare with 12 meters. Here you have a textural information that you can investigate. They are not really. And here we made some work on tropical forest for monitoring tropical forest. And so here, tropical forest with 20 meters of spatial resolution. Here with 1 meter of spatial resolution. So with 1 meter, you begins to discriminate each trees with its crown. And here the same in optic. And you can see that in optics, you have a color because you use a really wide wavelength range, while here the range is not so big, so you don't have this color information. This is synthesis here, 20 meters of spatial resolution, 1 meter in radar, and 1 meter in optical data. Do you have some questions? I just I had explained you very badly this, and I will show you a movie made by the CNES, which illustrates very well all I explained. Before, do you have any questions? Just, in fact, you don't need to be an expert of how an image has been acquired, by just remind that you have two directions. Range direction is the propagation of the direction of propagation of the pulse. Azimuthal direction corresponds to the move of the sensor. You have a difference between resolution and pixel size. The pixel size is always higher than the resolution. And to get a good spatial resolution, you need to have a large bandwidth. This is built in the range resolution. It depends on the bandwidth of the pulse that you build. So you build with the bandwidth you want. And in the azimuthal direction, you use the natural bandwidth, which is due to the Doppler effect.
Yeah, hi, I don't know if you can see me, but I was wondering if, so as the ground resolution depends from the from the angle of the satellite, right? So
Yes.
how do you ensure that it has each measurement has consistent resolution over the entire swath? As it should change over
Yes.
the angle with the angle.
Yes, it changed. Yes, it changed. So, you cannot. You in general, when you speak about the spatial resolution of a radar image in the range direction, you speak about the average resolution about in the middle of the middle of the swath. All right, but it's you need to keep it in mind. The spatial resolution at the beginning of the swath is not the same that at the end of the swath. At the end, the larger the incident angle, the better the spatial resolution on the ground.
Okay. So with every measurement, you have to take into account that on the
Yes.
sides it wouldn't be as accurate as in the middle, right?
Yes.
Okay.
And so, in general, it depends of the application. If you work on really large area, the swath of Sentinel-1 is 350 kilometers. So but a lot of people doesn't work with so huge areas. But if you are concerned with the whole scene, you have to keep it in mind. Otherwise, if you are just on a sub-region, it's approximately constant.
Another follow-up question would be: is there any way to correct it?
What do you know? No, it's a physical principle.
Yeah, I mean, but take into account. Yeah.
Of course, we will in the practical, we will ortho-rectify the data, and so we will get image in that will have been projected according map coordinates, and so all the pixels of your image will have exactly the same size on the Earth, but they are derived from spatial resolution that differs because it's like this with radar.
Okay, thank you.
Are there other questions? So I can show you this it's for 10 minutes and it's really interesting illustration. Is it okay? Can you hear it?
Yes, we can hear it.
Super.
The first radar imaging systems were only an extension of angular optical vision to the microwave frequency range, thus enabling all weather coverage. In other words, the possibility of seeing through clouds. As is true for all radars, they worked by emitting pulses. Each pulse illuminated a strip of ground. In this way, the system analyzed the landscape by successive swayings along the line of the aircraft's movement. Within each strip, the range resolution power is obtained by refined sampling of the echo during its return. As radar is an excellent instrument for measuring distances, one might legitimately expect good accuracy in this direction. However, azimuth resolution, that is, the resolution along the line of the aircraft's movement, is much less satisfactory. It remains equal to the width of the strip of ground illuminated, which itself is inversely proportional to the length of the antenna. Thus, even with a 4-meter-long antenna, like the one flown on this B-17, it is only possible to obtain a resolution of the order of 100 meters. The The idea then is to use the movement of the aircraft to simulate or to synthesize a large-sized antenna, whence the name of synthetic aperture radar, or SAR. This principle might make you think of the parabolic antenna networks used by the large radio telescopes, such as that of Socorro near Albuquerque in New Mexico. Optical telescopes with synthetic aperture are based upon the same principle. However, the distance between a fixed point on the ground and the radar varies with the movement of the aircraft. The echoes from this point will therefore not arrive with the same phase on the different elementary antenna. This phase variation will require compensation in order to synthesize the large antenna. This is the whole point of SAR processing. This blurred image is the image which is directly acquired by the radar without any processing. It is made up of raw data. This data will undergo successive processing until it is transformed into a sharp image which may be registered on a map. The first part of this processing includes the range and azimuth compressions and constitutes the actual image synthesis. The second part consists of geometric and radiometric corrections designed to eliminate the distortions due to the radar imaging technique. The radar emits a pulse perpendicularly to its flight direction. This pulse is successively backscattered by each of the targets encountered, and the echo is sampled and then digitized aboard the aircraft. The resolution obtained, in other words, the fineness of the details observed, is of course a function of the sampling frequency, but also depends on the width of the pulse emitted. In order to achieve a high resolution of about 1 meter, the pulse should only last a few nanoseconds. Technically speaking, this is somewhat difficult because of the power needed. The alternative, then, is to use a technique which is often employed by all kinds of radar systems, the so-called pulse compression technique. This means that the radar emits a long pulse, but with linear frequency modulation, which has the advantage of being compressible either directly through onboard filtering or by digital data processing, called correlation, on the ground. As we have seen, the SAR processing aims to reconstruct a large-sized antenna by adding together all the data acquired from one point, contained in all the echoes in which it has participated, normally a few hundred. We have also seen that the distances between this point and the radar evolve, and this has to be taken into account in order to carry out an in-phase addition. In fact, it is necessary to apply a phase shift correction contrary to that applied to the point by each elementary antenna. More precisely, it may be mathematically demonstrated that the radar target distance describes a parabolic curve. The corresponding phase variation is therefore quadratic. Now, a phase variation is a frequency. We therefore obtain a frequency with linear variation. This is more or less the Doppler effect, with a positive frequency when the radar approaches the target and a negative frequency when it moves away from the target. The frequency band thus described, called the Doppler band, will be determined by the width of the antenna pattern. Resolution is therefore simply inversely proportional to this frequency bandwidth and independent of the observation distance. We may now say that we have gone from angular vision to resolution in terms of a bandwidth which is closer to signal processing theory. Azimuth synthesis consists of predicting the phase variation laws on the basis of known image acquisition geometry and of correlating the data with these laws. We have seen that the radar target distance varies during image acquisition.
I think I stop here because what I want to say, if you are people who like signal processing, you can see that with radar you can have a lot of fun. Now, a lot of people, and I hope that most of people that will use radar images are not accustomed, are not don't understand very few things in signal processing. But you can, if you don't know this, it's not important. Just use the image. But you use the image in the same way that you can use optical data, and you don't know what is all the processing made on board with Sentinel-2 sensor. You have also a lot of processing that is hidden. In radar, it is not hidden because the spatial resolution and the pixel size are different. And I think it's the real point. So I will add a slide before transmitting you the documents to the main points. Just retain. And then you have two directions. The range direction and the azimuthal direction. The range direction corresponds to the propagating direction of the wave. And in the range direction, the natural geometry is the slant direction. And when you want to know what is the corresponding ground direction, you have to divide by sinus of the incidence. In the azimuthal direction, you have the pixel size, which depends on the speed of the antenna and the pulse repetition frequency, all right? And you have an azimuthal spatial resolution, which depends after the synthesis aperture radar processing, which depends only on the size of the antenna. Just remind, keep this in mind. Do you have some questions?
I don't think there are questions.
So, some few words about polarization. I won't speak about polarimetry because there is no full polarimetry system now on orbit. So each problem at its time. So just I explain a little more the polarization of a wave. A coherent wave, coherent means that you know how is the wave at one point, at one time in the space, and you know its behavior everywhere. So if I fix a point and I look at the evolution of the wave at this point while the time is going, I see, for example, this wave. So this wave is characterized by a certain period, which is called T, and an amplitude. So in a mathematical point of view, it's really easy. When you have something periodical like this, we use a cosine function. The frequency, which is the inverse of the period, you can introduce this here, and the blue wave here, which is characterized by this amplitude, and this period, this time period, is, you know it by this formula, all right, it's okay. Now, you have just another parameter characterizing a coherent wave. It is when you look at the red wave, it's exactly the same than the blue wave, but there is a shift, there is a delay, horizontal delay. And this corresponds to something which is proportional to what is called the phase. All right, and so the difference between in a mathematical writing, the difference between these two draws are just this phase. All right. So what is characterizing a coherent wave? Its time period, so its frequency, and its amplitude and its phase. So this is when you fix a point and you look at its evolution during the time. When you look at, when you do the same, if I take a picture of my wave at a given time, you will have the same, but now you will see the evolution in function of a spatial direction. All right. And so you will see exactly a period, which is called the wavelength, and an amplitude, which is the same, and maybe a phase. All right. And so you see that this wave is characterized by a temporal period, which is related to the spatial period with the speed of propagation, and an amplitude and a phase. So you have three characteristics of a coherent wave: its frequency, or its period, or its wavelength, and an amplitude and a phase. So this in mathematics, we combine all these things by, this is the amplitude, the frequency, which is related to the wavelength here, and the phase. So when you record an echo, the system, the antenna operates at a given wavelength or a given frequency. They are related. So you know this, but you just have to record two characteristics: the amplitude and the phase of the coherent wave backscattered echo. So these are the two characteristics that you have to record by contrast with optical sensor, where you just record the amplitude because you don't have coherent wave. You have billions of coherent waves during the integral time you use, and so you just record an average amplitude in optic, while with radar with coherent wave, you have the amplitude and the phase. What is the polarization? The polarization is just the geometrical location, trajectory of the extremity of the electric field while the electromagnetic wave is propagating. So when the electromagnetic wave is propagating, the electric field and magnetic field, which is orthogonal, are always moves always in the plane which is perpendicular to the direction of propagation of the wave. And the most general polarization for a coherent wave is an elliptical waves, an elliptical polarization. So when you have an elliptical polarization, you can play over the flatness of the ellipse and the direction of the big axis. So when the ellipse is totally circular, when you don't have minor and major axis, you just have a circle, you speak about circular polarization. And you can also have this ellipse totally flat, and in that case, you speak about linear polarization. And it is linear polarization that we speak about in remote sensing, in radar remote sensing, because all the spaceborne radar sensors use linear polarization, as I was explaining you. So the same. Then another slide to explain exactly the same. So this polarization depends on the incident plane. You have both letters for reception and emission, which so one acquisition is always characterized by two letters, two polarization for emission and reception. So the polarization is very important because when you have a surface with vertical structures, these vertical structures will interact a lot with a vertically polarized wave, while an horizontal polarized wave won't interact a lot with vertical structures. And so here, just I show you a spectacular illustration. This has been done with NVSat sensor. NVSat was between ERS sensors and Sentinel-1. He used a lot of services to everybody. And so this is a forest in Brazil. And the ASAR sensor on board NVSat satellite operated in two polarization. Here you see the HH polarization, and the same scene was acquired in the same time in HV polarization, because it emitted the H polarization and received in this recorded in the same time the H and V component of the backscattered echoes. And so you can see in HH polarization, you can see very well these bright features here, which corresponds to flooded forests. And so this is because this polarization doesn't interact a lot with the trunks and the branches, which are quite vertical. And as it's horizontal, it doesn't interact a lot and sees the ground under the vegetation. And when this ground is very reflective due to water, you see this with bright areas. You can see here some dark areas corresponding to deforested areas. And now if you look at HV polarization, you can see that in HV polarization, the contrast between deforested areas and forested ones are much more highlighted. And so if I'm looking for mapping deforested areas and monitoring the deforested areas in these regions, I will better use HV polarization. But here with HV polarization, I cannot see anymore the flooded forests. Here in French Guiana, they made a dam, and when they built the dam, the water flooded the relief, and these trees, the existing trees, was not able to live with their feet in the water, so they died. And then you get just only the trunk. And so it's the reason why with and so it's the reason why here in HH polarization again, you can see all this lake due to the dam, which is really bright, and it's not the case in VV polarization. Also, difference of polarization, HV and VV seen by ASAR on board NVSat. This is in Gabon, and you see that in VV polarization, when the ocean is quite rough, you cannot see the shoreline, while you see it really easily with HV polarization. These both acquisition is made at the same time. Huh? Here, if you have people interested in forestry, we made a study and we were interested in a French Polynesian island only constituted of different forest types. And in HV, HH and VV polarization with the same wavelength, just with 3 different polarization, you can see that you can discriminate such very different type of vegetation, type of forest. And we were able to produce vegetation maps. And here for 4 different forest types, because the polarization is very sensitive to the geometry of the scatterers, and these different trees has totally different geometrical structures. That was very useful to discriminate them just with different polarization. So just to close this chapter, when you use intensity or amplitude image, what we are going to use with Sentinel-1 GRD products, in general, because a lot of people, a lot of students ask me, so what is the best polarization? The best, I don't know. But you know that you have some polarization better fitted than others for different type of scattering mechanism. When you have different polarization, always look all the polarization, because you have always good surprise. But in general, when you have surface scattering, just when you don't have vegetation, just bare soil, in general, with VV, you have cross polarization here, which is very low, almost not so interesting. But you have VV and HH, which gives information. And in general, VV is very sensitive to the roughness of the soil or the roughness of the water. When you are interested in over dense forest, approximately all the different polarization has the same behavior, but you have a very large contrast between low vegetation with cross polarization very low and dense vegetation with cross polarization very high. So this is HV polarization is quite good for forest and no forest discrimination. When you are interested with double reflection, like the lakes I showed you, or over urban areas because of the buildings and the streets, in that case, HH polarization is very discriminative. And when you have everything, when you have something totally messing everything, when you have disorderly rocks or urban areas, but with no structure, directional structure like in American towns, you will have approximately the same response with all the different polarization. So VV polarization, nice for bare surfaces and vegetation with vertical structures, HV polarization for discrimination of the forest, non-forest, and HH polarization for flooded, non-flooded vegetation or urban areas. I stopped because after it concerned polarimetry, and what we see is the difference of the response according to different type of polarization. And so we stopped for this. Do you have some questions? 13h37, we have 25 minutes. We can just, before I continue with some theory, we can show some, look at some radar data. So radar data, how do I do it? We are going to process some, to look at some radar data with SNAP, all right? How do we do it? For example, I do it again. I have my same, wait a minute, how can I do? I don't know how. I do it again. I go to the ESA hub. Open hub. I'm lost. Riga is there. This, I go here, and now for the sensing period, I just take the last one. Oh, we won't have so much data because you have only one satellite. And here, what are these? Raw data. Raw data. Raw data corresponds to this one. I never use it, and I hope I won't never use it. No, excuse me. It's not this one. It's other. It's not either an image. So really, you forget it. Raw data are just the raw echoes that reach the sensor. No, excuse me. I'm lost. I'm here. So raw data you don't take. Single look complex, SLC for single look complex. Complex, why? Because complex means two parameters to define a complex number, the amplitude and the phase, because these are coherent waves, so you have amplitude and phase. But I don't care about this, and I will take the ground range detected product. I will explain you. So ground range. You know what does it mean, ground range? It means that you are not anymore in the radar geometry, but you have projected it on the flat surface. And detected means you just get the amplitude or the intensity. Sorry, I forget to tell you something. Here, A is the amplitude. And the intensity is just this, the square of the amplitude. So it's the same, all right? When you have one, you have the other one. So speak about amplitude or speak about intensity, you have exactly the same information in the image. Huh? Are you okay with this? Yes? Or who is not okay? So it is not to frighten you. Huh? It is just because those who are not okay I'm more interested in those who are not okay to explain this So again here, ground range, because I have divided approximately by the sine of the incidence angle to get the ground geometry. I projected the slant range into the ground range by divided by the sine of the incidence angle. Detected means I have lost my phase. I just take amplitude or intensity, and so I'm quite close of an optical image. Huh? It's in the same format. Sensor mode over lens surfaces, you just have interferometric wide corresponding to 350 kilometers of wide swath. And all the polarization, and it's okay. And I log. Oh. And I have all these ones. For example, this one, I like it. What is it? This one. For example, this one, if I look at it, oh, incredible, a radar image which is not black and white. Yes, because thanks to Sentinel-1, we have two polarization. So you put one color channel in one polarization, the other in the second, and the last polarization, you make the ratio between both polarization and you get your 3 color channel. So you can get this, and you download the product, and you get it. So now let's go to Snap. Oh, does the people who ask me the difference between NDVI when I compute it and when I don't compute, and when by my own with a raster calculator or by thematic lens là, with here. Is it here? Is he here? Because I tried this during the lunch break, and I have exactly the same values. Huh? So really, to these people, if you have an exception, send it by email. Huh? I will look at.
Okay, it was a slightly different question. It's how do you deal with raw Sentinel-2 values, because there's no fixed range. So Sentinel-2, the reflectance it could be from 0 to 6,000, 7,000, 8,000. And how do you deal with these dynamic values? Because Sentinel-1 has the same problem with the backscatter. The backscatter doesn't have a fixed range. So if you're working practically with this raw data, then how do you scale it up? And that's what the question. But I'll send an email to
all right, so I'm sorry, but I don't use any raw data because my skills are not in signal processing, and so I don't use any raw data either in Sentinel-2 or Sentinel-1. Me, I'm focused on application of remote sensing data for tropical forest monitoring, for agriculture crops monitoring, and so I don't. I use just already calibrated products, and so I can use single look complex products for radar. Most of time I use GRD product. Single look complex, I will explain you what is it. And GRD product I use most of time. And with Sentinel-2, I didn't see that. Wait a minute. With Sentinel-2, what do you call raw data with Sentinel-2?
So, for example, Sentinel-2 band values they're measured in either reflectance or in dynamic numbers. So if it's reflectance, then it's usually between 0 and 1. If it's dynamic values, it's dynamic numbers, then it's between 0 and it could be 6,000 or above. So like that's, yes. So if you read in the actual values, that's what you see.
Yes, so here I have just look at I have opened, we will do it, maybe, I don't think we will have time, unhappily, because it would have been very interesting. For example, here, these are the 2, 3, 4, and 8 band of Sentinel-2, and look at the values. You just have to divide by 10,000, and you get the reflectance value. So these values, all right, it's in digital number, but they are already calibrated in reflectance.
Yes, and the issue is that for multiple time series of images, the range of these values are not fixed, so the range can vary very, very greatly. And
yes.
Exactly, so that's what my issue is. And it's the same problem with Sentinel-1 and Sentinel-2 as well. So how do you scale these values reasonably so that you have consistent model outputs if you're working with them?
So when you have such variation with Sentinel-2, this is most of time due to atmospheric perturbations. Mm-hmm. And this is the big issue with optical data, and you have to do the best with this. There is no magic solution. You have to do the best with this. With Sentinel-1, you have a wide range of variation because radar reflectance has a huge dynamic, but it corresponds to change on the Earth surface state. So it's really valuable information, these variations. And so I don't want at all correct the variation in Sentinel-1 values, because they correspond to the real variations of the observed scene. With Sentinel-2, because of the difference of atmosphere states, this is much more complicated.
Okay. And from your experience with Sentinel-1, have you seen cases where the amplitude has changed for other reasons that has nothing to do with changes on the ground, for example? So like, let's say across the years, maybe in different styles in which the data is being processed, you have different amplitude values from the same area.
No.
Okay.
If you have different amplitude, it is not because, oh, all right. Spaceborne remote sensing data are delivered by spatial agencies. So it's really hard working, and it's a processing very heavy. And so you can be confident with the values that you get. So sometimes you can see some data that are really strange. I saw it once or twice.
Okay.
So in that case, I asked to the help desk of ESA, and they told me, all right, yes, there are a problem of calibration, and so, but you can see it quite easily. And the best way is to remove this data in this case, because you can, if you begin to compensate error of calibration, you will have other errors or something like this. Did you get strange value often?
So sometimes. So that's my issue. Like I've been trying to, I get strange value sometimes from Sentinel-1. I speak to the data experts and I don't get any response. And I've been trying to find what's the best way to validate Sentinel-1 data to make sure that if there are changes or if there are strange scenarios, you can explain them, because if not, it affects the model output. And you get like, because I use these values in modeling, generative modeling or crop yield prediction. And if I get strange outputs there, then mostly it has to do with the data, not the model. So that's why I'm asking these questions.
You use a GRD product or SLC product?
SLC for Sentinel-1, SL2A for Sentinel-2.
So with SLC, you can analyze the coherence value, the interferometric coherence between the two consecutive data. Mm-hmm. And you will see if you have no coherence at all everywhere, you see that you have data which is not okay. And then also by analyzing the temporal profile of in the three polarization, VV, HV, and also the ratio between VV and HV.
Okay.
And with this, it's quite easy to see if you and also, of course, you have to look at your data. Sometimes because you have three subswaths with a Sentinel-1 interferometric wide mode. And sometimes you see that you can identify a swath. In that case, it's sure you have a problem of calibration.
Okay. That's really good. Thank you.
You're welcome. Yes. So let's go again. And you saw how I select the Sentinel-1 data. And now, when I download it, you can go into data Sentinel-1 zip here. So data Sentinel-1 zip folder, and in this folder you have 4 Sentinel-1 data. So when you take snap, which is here, so first we are open one data only in snap. So first you close all the products because it corresponds to the optical Sentinel-2 data. By the way, I forgot this morning just to tell you, have you seen all the vegetation? Because it's an area with a lot of vegetation, and you have not only the clouds, but also the shadows. And this is very a big issue with optical data. So when you look at this and you take the vegetation index, the vegetation index, you can discriminate very well all the clouds and their shadows, which appears totally dark because both red and near red infrared are very high. So when you make the difference of two very high numbers, you have something close to 0. So just now, close file, close all products. It's okay? I don't want to save anything. Then take one zip file. So you see it's Sentinel-1B, interferometric wide, ground range detected, high product, because you have high and medium, but in general it's always high. One SDV, I forgot, I'm sorry. D for dual, two polarization. I forgot what does it mean. And here you have the acquisition time, the 25th of April 2017. The beginning was at 9 p.m. 42:34, and the end of the acquisition was 9 p.m. 43 and 2 seconds, 43 minutes 2 seconds. So yeah, just drag and drop in a snap, and you can look on metadata, and you have a lot of things here. You can see that it's Sentinel-1B, acquisition mode, interferometric wide. The antenna was pointing as usual because it's always like this with Sentinel. It points on the right side of the direction of the movement. You have the relative orbit. We will speak maybe about this. Relative orbit corresponds to each orbit after 6 days. The satellite goes on the same orbit, 12 days. After 12 days, the satellite recovers its first orbit. So all these orbits that it has made during these 12 days are counted and have a relative number. So this is the relative number which corresponds to the position of the satellite on the orbit. Then incidence of near range, so the closest of the swath. It's, I told you, about 30 degrees. The far range, 45 degrees. Then first line time, the first line, so it's the first acquisition. It was at 9 p.m. 42. The last line, 9 p.m. 43. And now you have the latitude, longitude of the four corners of the incident of the image. So first line near range, far range, last line near range, last line far range. Then you have, it is detected, so you will have only amplitude or intensity. And so then Wait a minute. All right, the number of loops, we will speak about this. The range spacing, it is the pixel size of a range in the range direction. Azimuth spacing in the line size. This is a column size. And so this corresponds to the ground range because it is GRD product. And maybe it's this. You have the azimuth bandwidth, which corresponds to the Doppler bandwidth. The range bandwidth, which corresponds to the bandwidth of the pulse that have been built. So you have everything. Now you can go to bands, and you have amplitude in VH and VV because you have two polarization. And you can see that you have also intensity. And you see a V, which means virtual. Of course, you don't need to take a place on your disk because amplitude is just, the intensity is just the square of the amplitude. So if you have one, so you can look at what is this. Aha. All right. And in VV polarization, all right. So, for example, the people who told me that he had some strange values just asked me the question. For example, here you see the three subswaths which compose the interferometric wide mode of acquisition. So if you see it, you see, oh, there is some problems. No, it's just some problems at the junction, and you see it on the ocean because, but over the land, you don't see any, you shouldn't see any difference between, or if you see it on the land, you would have some calibration problem, but you won't do the same calibration on the ocean than on the land. And as here you are on the land, it is the land calibration process which is used. All right. And now, what did I want to see? You can so if I go, do you have the world view here? Do you see the globe when you click on the tab world?
Yes.
You're lucky. I never get it. It's better. What is better like this? I prefer that you have it than me. So here, if you go to navigation and you click here to get the full resolution, you can see the differences between VH and VV. All right. In polarization, different polarization, you have different response depending on the surface state. We have to stop. It's a coffee break, Amalia.
We have it at 3 o'clock. I don't know what time it is now. It's 3 o'clock. Then it's time for the break. Yes, if this is a good time for you.
Yes.
Then,
Yes.
yeah.
Is it a good time for the participants also?
I think so. And then we will be back in half an hour. So 3:30
right.
for us, 2:30 for you.
My main purpose is that participants keep alive. Huh?
Yeah, no questions so far.
All right.
See you later.
See you later.